Hello, my name's Ryan, and this is a presentation behind my honors project submitted for my cybersecurity degree here at Glasgow, Caledonian. The topic we've researched is evaluating lightweight cryptography for secure firmware updates in smart home IoT. To introduce you to the topic, the scope of it is smart home IoT devices. So, your smart TV, your smart camera, your smart light bulb, anything in your house that's connected to the internet, quote unquote smart device, is not very smart. These computers are very resource strained, um, and that means they struggle to implement security features such as cryptography, right? IoT devices are notoriously vulnerable, and it's down to the vendor to decide how to they can maintain operational efficiency whilst having that security. Firmware updates. So firmware is the code within the non-volatile data of these devices that allows these IoT devices to function as they should. Um, it's the piece of code which the vendor creates that allows it to function as required. So the firmware update, as you can imagine, is just updating that and the process of taking the firmware from the vendor and putting it onto the IoT device. And this can be for device maintenance, it can be for patching exploits, but it's a very, very good attack vector for bad actors. Um, we're investigating lightweight encryption. So in that process, we want to encrypt these files, and lightweight cryptography seems suitable for such resource-constrained devices. Leads us to this research question. Which lightweight cryptographic protocols offer the optimal balance of security and performance for firmware over-the-air updates in resource-constrained smart home IoT devices? So, to keep you interested, these real-world cases, in 2016, the Mirai botnet, super famous, hacked over 1 million devices, mostly cameras, and then because of that, the Mirai botnet was capable of launching DDoS attacks exceeding a terabit per second. In 2020, the SolarWinds supply chain attack, over 18,000 organizations were hacked, and was undetected for 9 months. $100 billion financial impact and over 1,000 engineers to remediate. There's no undermining how much damage that caused. So to give you context into my research and my methodology, here are the chosen cryptographic approaches I am using. AES-128, Advanced Encryption Standard. Uh, this is like your bog standard, you've probably heard of this, implemented in early mid-2000s. CHA-20 is also symmetric. It's pretty much a more modern version of AES-128, encrypts in streams over blocks. Um, then we get into elliptic curve cryptography, so elliptic curve digital signature algorithm, ECDSA. This is asymmetric and has signature checking. ED25519 is also asymmetric and it is based on the elliptic curve 25519. This was implemented in 2015, 2016, and is the most modern protocol here. This hybrid approach, we have CHA-20 symmetric encryption paired with elliptic curve Diffie-Hellman key exchange. And this hybrid approach, we predict, is going to maintain the performance advantages of CHA-20 whilst having that secure key exchange in elliptic curve cryptography. At the top, here's a diagram showcasing symmetric keys using the same key and asymmetric keys using different keys. So our experiment, the network methodology, we have 3 virtual machines in VMware. They're not real devices, but we do connect them to a real guest Wi-Fi network because IoT communicates over Wi-Fi. These devices are the IoT device with Ubuntu Core operating system, the firmware update server, which is Ubuntu, and then a Kali Linux advisory machine. And here is the network topology. As you notice, the attacker is the gateway for the IoT device. What are we measuring? What do we care about? We care about the IoT resource usage, so the CPU and memory usage during encryption and decryption and receiving an update. Any delays introduced by encryption or decryption. The firmware update server resource usage, so that's CPU and memory deploying an update. how long these updates take, and how resistant they are to attacks. Uh, to output this and analyze this, we have CSV files. Uh, they are automated. All the results are automatically put into CSV files. And then we can use Google Sheets and conditional formatting to interpret that data and create graphs where relevant. Our experimental setup, the baseline is we use a lot of scripting with Bash. All these shell scripts, there are a total of 9, and they do as they say. So this generates the firmware, generates the keys, encrypts the firmware, and then uploads the firmware to the web server. And then the IoT simulation makes it act like an IoT device, putting resource constraints on it. Firmware listener allows for the update to happen. Then the adversary machine has its adversary scripts. The advantages of using a bash script automation process like this is that it's very reproducible, results are simple to gather, and it's very easy to use with Linux. So, in order to have our IoT VM act as an IoT VM, right, we need the IoT simulation script. We need it to represent a real device. Here are the limitations that we implemented, and we used the CPU limit tool, for example, to implement CPU throttling of 70% execution cap. Here is the entire firmware update workflow. So the server generates keys, generates firmware with the firmware generation script, encrypts all that firmware, and then it sends it to the IoT device over UDP port 9999. That's the important bit, because the IoT device is listening on that port. It does its security checks, and then it either accepts or rejects it. Here is an example of what you would see on the IoT device upon a successful firmware deployment. And then the attack vectors we are investigating. We have a man-in-the-middle attack, so getting that adversary between, poisoning the target device's ARP caches in order to redirect traffic to itself. A replay attack, which is when you replay old captured network packets back into the network and hopefully mess with the IoT device or just cause chaos. And then we have a downgrade attack. So our experiment, we didn't have any versioning within the updates, mainly because we wanted to test the cryptography defense mechanism instead of the firmware itself being able to recognize, the IoT device itself being able to recognize that versioning. So we just deploy modified firmware in the place of a downgrade attack, and we can argue that acts cryptographically the same. I do have a live demo here. At first, you'll see the IoT device executing the firmware listener script. It's waiting for updates over port 9999. Here we go over to the photo server. We're going to upload firmware here. It prompts you what encryption protocol you'd like to use. Here's a directory with our firmware inside of it. And it sent a UDP notification to the IoT device on port 9999. The IoT device hears this, and then you are able to install it. That's pretty much the premise of it. Okay, our experiment's over. What were the results? So, in terms of encryption and that initializing of firmware, symmetric encryption underperformed. Asymmetric was that many times quicker, 5 to 12. And it used less CPU and memory, of course, right? So in terms of the photo server resource usage, asymmetric proved very great. Decryption metrics from the IoT device proved the exact same results, which is nice. In terms of total update time, Cha-Cha 20 was ahead. It was the expected winner and was the winner. The hybrid approach we created, it underperformed. We did not expect it to have the longest update time due to our symmetric encryption implementation. However, at larger firmware sizes, it is suspected that the network transfer and the network latency, things out of our control, probably had more influence than we realize. So that reinforces the idea that protocol choice is more important for smaller firmware sizes, for smaller firmware updates. So security analysis, these man-in-the-middle attacks, the results were consistent because HTTP was the transport protocol. We did not have a PKI or HTTPS, but it could be argued that although all the traffic could be sniffed and read, all the encrypted files could be read, for the symmetric cryptography, these files are susceptible to brute forcing, and that is a very real thought or possibility when it comes to something like quantum computing, where these keys can be broken. Symmetric cryptography will be dated, so we've scored it higher in the risk matrix. Here's what the adversary saw with man-in-the-middle proxy. Replay attacks. So we had a replay prevention measure in our firmware listener script, and it did reject the updates if they were over an hour old, as the replay attacks were over an hour before they were relayed back to the IoT device. This worked, so there's no vulnerability here. As you could see, the IoT device rejects the update if it cannot verify the timestamp. Downgrade attacks, so deploying modified firmware, this is the big one. So it was not possible with digital signatures because the public key does not match the private key of the legitimate photo server if it's from the adversary. And in symmetric encryption, modified firmware was deployable. In terms of asymmetry and signature checking, this did not happen. Here you can see the AES 128 being able to be deployed despite it being modified firmware. It passes security checks. So what do we know? ED25519 emerged as the most optimal solution. It provides both robust security and great performance. ChaCha20 was faster though, and if it was the case that an update needed to be pushed quicker, then ChaCha20 could be argued in that sense to be better. Here's a risk matrix though, and in my opinion, symmetric cryptography, having such a high risk is just not ever worth it. In terms of societal impact and social goals, we align with SDG 9 and SDG 12. We want to build resilient infrastructure and ensure sustainable consumption and production patterns. So we want to improve public confidence in IoT because it can be very scary. It's very warranted that there's all these attack vectors, and we want IoT to be implemented in more use cases because it can be very good. The uptake of IoT drives energy-saving smart home systems. This assists climate change, and literally choosing a better protocol to encrypt and decrypt with is optimizing energy performance of the firmware update itself. Our research helps improve developers' time at creating IoT firmware and implementing cryptography in their firmware updates. I really appreciate your time. Sorry if I talked very quick. I wanted to get that in. But here's my GitHub link, and I am hoping to put up a informal write-up on here very soon. So check that out. And I really appreciate your interest in my research. So thank you.